All right, good morning, guys. We're going to go ahead and begin our next lesson on inverse functions. And this lesson is probably going to span the entirety of the week. Really dense lesson, a lot of important stuff in this lesson, and a lot of important stuff that we're going to use as we continue moving through this unit. Okay, so before we start talking about inverse functions, let's go over what a function is once again. So a function is defined as a relation, which a relation is a set of ordered pairs, where each element of the domain gets assigned to exactly one element of the range. Okay, so that's what a function is. Something that's going to be important for us in this lesson is a special type of function called a one-to-one function. So a function is one-to-one, so I'm going to abbreviate one-to-one moving forward as 1-1 if any two different inputs never correspond to the same output. Okay, which another way of saying that is that each x value gets sent to or gets assigned to a unique y value. All right, so what we're going to do first is we're going to take a look at an example, just making sure that we can make the distinction between, hey, is a relation a function? And if so, is the function one-to-one? Okay, so to start out with, we have our set of domain values. So this is what's called like a mapping. So when you see the domain value of 0 with an arrow to the range value of 4, that means that this relation contains the ordered pair 0, 4. When you see 1 going to 4, it also contains the ordered pair 1, 4, and so on and so forth. Okay, so when we look here, to answer the first question, is this relation a function? The answer is yes, because we have each domain value only going to one range value. We don't have a domain value that goes to two different range values, which would indicate that this is not a function. So this here is a function. And then the second part says, if so, is the function one-to-one? This function here is not one-to-one. And the reason being is that we have these two domain values of 0 and 1 getting sent to the same range value. So for the function to be one-to-one, each domain value has to go to a unique range value. You can't have two domain values that go to the same range value. Okay, second example. We have the relation whose domain contains the values 0, 1, 2, and 3. And the range contains the values 4, 5, 6, and 7. We have 0 being sent to 6, 1 being sent to 4, 2 being sent to 7, and 3 being sent to 5. Okay, so is that relation a function? Yes, the relation is a function, because each domain value only goes to one range value. And then this function is also one-to-one because each domain value goes to a unique range value. All right, so there are no two domain values that go to the same range value. All right, and the function being one-to-one is going to be of great significance to us. In this section, we're going to talk about what that tells us about the function momentarily. Okay, so for all one-to-one functions, the inverse function is the set of ordered pairs obtained by interchanging or swapping the first and second coordinates of each ordered pair in the original function. Okay, so if we want to find the inverse of a function, we can do so by switching the first and second coordinates. So the first coordinate refers to x values, the second coordinate refers to y values. So we're going to switch the x and y values of each ordered pair in the original function. Okay, if f of x is the original function its inverse is denoted as so. Okay, so this is how we write f inverse of x. Looks like f, and then it looks like the exponent -1. It's not an exponent, but that's how we write the inverse f inverse of x. Okay, now a couple of things to keep in mind in regards to inverse functions. Number one is not all functions have inverses. And number two, the inverse of a function may not always be a function. Okay, so the original function must be 1-to-1 for its inverse to be a function. Okay, so again, the original function must be 1-to-1 for its inverse to be a function. Now, with that said, I'm going to go back and revisit the examples that we looked at to start this lesson off. Okay, so if we go to the first example that we looked at, if I want to find the inverse of that function, we do so by switching the first and second coordinates, so by switching the x and y values. So what does that mean? That means that the range of the original function becomes the domain of the inverse, because range refers to y values. When we switch the x and y coordinates, the range becomes the domain. And the domain, when we switch the x and y coordinates, is going to become the range. Okay, so the range is going to contain the values 0, 1, 2, and 3. Now the domain value of 4 is going to get sent to the range values of 0 and 1. So the inverse here is not a function. And the reason being is that the original function is not 1-to-1. So if your original function is not 1-to-1, when you switch the x and y coordinates, you're going to have some x values that go to more than one y value, indicating that that is not a function. Okay. For number two, if we wanted to find the inverse here, our domain would contain the values of 4, 5, 6, and 7. The range contains the values 0, 1, 2, and 3. So 4 is going to get sent to 1. 5 is going to get sent to 3. 6 is going to get sent to 0. And 7 is going to get sent to 2. And we have each domain value only going to one range value. So this here is going to be a function. Okay, so again, the original function must be 1-to-1 in order for the inverse to be a function. Okay, so graphically speaking, and we've talked about this already in class, to determine if a graph represents a function, we perform the vertical line test. Okay, so again, to determine if a graph represents a function, we perform the vertical line test. So an example of a graph representing a function is if we take the graph of the function y is equal to x squared. That's a parabola opening up. No matter where we draw our vertical line, that vertical line is only going to intersect the graph in one point. Okay, so this right here is going to be a function. If we think about a graph that we've looked at in class this year that is not a function, we can take, for example, a circle. So let's say we draw a circle over here, like so. When we draw a vertical line passing through the circle, unless we draw it at like the very edges of the circle, it's going to intersect the graph in more than one point. So this here is not a function. Okay, we can also graphically determine if a graph is 1-to-1. And if we want to determine if a graph is 1-to-1, we perform the horizontal line test. So vertical line test was we draw a vertical line. If it intersects the graph, if any vertical line intersects the graph in more than one point, then that graph is not a function. The horizontal line test says if we draw a horizontal line and it intersects the graph in more than one point, then that graph is not one-to-one. So an example of a graph that we've looked at in class that is one-to-one could be something like this. The function x cubed, like no matter where we draw the horizontal line for this graph, it only intersects the graph in one point. Okay, so this one here is one-to-one. There are a couple of examples of functions that we've looked at in this class that are not one-to-one. We can take the function that we looked at up above, x squared. That is a function, it passes the vertical line test, but it's not one-to-one because if I draw a horizontal line anywhere except the vertex, it's going to intersect the graph in more than one point. Okay, so this is, excuse me, not one-to-one. Another function that we looked at in class that is not one-to-one, way back at the very start of class, is the function the absolute value of x. Okay, the absolute value of x, if we draw a horizontal line anywhere except at the corner of that graph, it's going to intersect the graph in more than one point. So again, this is not one-to-one as well. Okay, so just to build a little bit more on what we mentioned earlier, if we know the domain of the function f, that gives us some information about f inverse. The domain of f is the same as the range of f inverse. Because again, to go from a function to its inverse, we're going to switch the x and y coordinates of every single point. So all of the x values in the function f become y values in f inverse. And similarly, the range of the function f is going to be the same as the domain of f inverse. Because the y values in the function f, when we switch the x and y coordinates of every single point, that becomes the x values in f inverse. So that's the domain of f inverse. Okay, so last thing that we're going to go over in today's lesson, and then we'll continue this lesson in class on Wednesday and Friday. We're going to talk about how we can verify that a function is one-to-one algebraically. Okay, so if we want to verify a function is one-to-one algebraically, the way that we do that is we must show that if f of a and f of b are equal to each other, that implies that a is equal to b. Okay, so again, if f of a and f of b are equal to each other, that means that a has to be equal to b. All right, so we're going to do just two examples illustrating this. First one asks us to show that the function f of x is equal to 2x plus 7 divided by 4. We want to show that that function is one-to-one. Okay, so f of a being equal to f of b. All right, we're going to start with that equation. So f of a is going to be 2a plus 7 divided by 4. We're going to set that equal to f of b, which is 2b plus 7 divided by 4. And then we're going to algebraically manipulate this equation and see if we can get a is equal to b. Okay, so what I can do to both sides of this equation to start with, I can multiply both sides of the equation by 4. When I do that, that's going to give me 2a plus 7 equal to 2b plus 7. Okay, so again, I'm going to try to isolate a and b on both sides of the equation. So next we're going to subtract 7 on both sides. So when we subtract 7 on both sides, we get 2a equal to 2b. And then the last thing I can do on both sides of the equation is divide both sides by 2, which gives us a is equal to b. So since we were able to start with the equation f of a is equal to f of b, algebraically manipulate it where we wind up with a being equal to b, that means that therefore, so that triangular set of dots mathematically means therefore. We can say that f of x is 1 to 1. Okay, last question of the day. So is the function f of x equal to x squared 1 to 1? So when we do the same thing, we are going to start with f of a being equal to f of b. So that means that a squared is equal to b squared. And then we're going to like algebraically manipulate this equation to see if that gives us that a is equal to b. Okay, so what I can do with this equation is I can take the square root of both sides. When I take the square root of a squared on the left-hand side, that gives me the absolute value of a. When I take the square root of b squared on the right-hand side, that gives me the absolute value of b. So that means that plus or minus a can be equal to plus or minus b. What it doesn't give us is that a is equal to b. So this here is not 1 to 1. And the reason that it's not 1 to 1 is it is possible that a is equal to plus or minus b and negative a is equal to plus or minus b. So it is, I mean, it can be where a is equal to b, but it's also possible where a is equal to negative b as well. Okay, so that does not give us the conclusion that we were hoping for, where when we set f of a equal to f of b, in order to be 1 to 1, it has to give us that a is equal to b. Okay, and that's not the case for this example down here. Okay, so this one here is not 1 to 1. All right, so that's what we're going to wrap up for today. It kind of gives us an introduction a little bit into inverse functions, how we define inverse functions, how we denote inverse functions, and we're going to do a ton of stuff with inverse functions the remainder of this week. All right, hope you guys have a great rest of your day.